Good afternoon, everyone. This session will be about a number of practical examples of successful optimizations implemented in Cachegrand. What is Cachegrand? Let's start with that. Cachegrand is a super scalable key value store that aims to be a Redis drop-in replacement. To achieve better performances, it's written in C and it's Linux only. Rust will be introduced down the line for higher level business logic. It has been built following two very simple guidelines: performance first and being data-driven. It's still a work in progress, although the first release is just a few weeks away. Performance first means that development is driven by performance goals. C and GCC have been chosen as the alternatives lag a bit behind in terms of performances and optimizations carried out by the compiler. With C, it's easier to have control over custom memory allocators and to use fibers. I've also preferred to develop a number of tailored implementations optimized for the use case at hand instead of ready-to-use libraries. And also, I prefer to focus on the most recent CPUs and hardware instead of having a wide support. Cachegrand is being developed trying to exploit the hardware and the OS as much as possible. Data structures organized in a convenient way for the CPU, taking advantage of cachelines optimized algorithms, avoid sharing memory between threads if possible, and as well keeping the threads pinned to a specific core. Reduce or entirely avoid syscalls because on a scale, the time spent switching between user space and kernel space is an absolute killer, and also prefer cooperative scheduling to take advantage of fibers whenever possible. The second guideline is being data-driven. Optimizations come with a cost. So how do we figure out what's worth and what's not? Modern compilers are able to carry out impressive optimizations thanks to static analysis, vectorizations, and etc. So it's extremely important to bench the code and bench the optimizations to ensure that the extra complexity is actually worth. Google Benchmark comes to the rescue from this point of view. It's a great library and it really helps to implement micro benchmarks. And there is also an online web service called the Quick Bench. It's great to run, as the name says, quick benchmarks using Google Benchmark. Although it's really important to keep in mind that those benchmarks are running on a virtual machines on the cloud, on Amazon. So the hardware varies and the virtual machine is impacted by noisy neighbors and other problems that are often faced on the cloud, so that the results can be really unpredictable. Say that it's important to keep in mind that a micro benchmark that shows a 500% speed improvement doesn't really translate to the same speed bump in a real use case. A micro benchmark does only one set of specific operations millions of times. An application usually does way less and perform additional work as well. It's also important to keep in mind that benchmarks can vary on different architectures. So it's important to use different CPUs, different generation of the CPUs, and different architectures of CPUs like Intel and AMD. And also to test on the cloud, especially because virtual machines tend to trash the CPU caches, and it's even worse with noisy neighbors. Cachegrand uses a number of different optimizations, memory fences over atomic operations if possible, fibers over west threads, and short strings optimizations. As well, it takes advantage of a parallel hash table built from the ground up to provide lock-free and wait-free get operations, with the set and delete operations relying on localized locks to avoid tombstones. It also takes advantage of a Slab allocator. It's only for Linux because it requires huge pages. And it's able to perform allocations and freeze in big O of 1. And also it takes advantage of IO ring, again Linux specific, to reduce the amount of syscalls needed for the IO. One of the main optimizations in Cachegrand is the use of fibers. It's also a great alternative to the well-known callback hell, very common in async applications that don't use multiple threads, fibers, or similar approaches. The context switching carried out by the OS performs a crazy number of operations. Even in recent kernels, where everything is very well optimized, it takes quite some time. In a software that needs to provide high performance, it's better to keep it at the minimum. Context switching takes about 1.4 microseconds, so with thousands of threads that keep switching, those numbers really matter. They can really impact the performance of an application. In this context, fibers come to the rescue, and they can provide a massive performance benefit if used in a smart way. Cachegrand and in most applications, the fibers don't really need to manage the signals, and if cooperative context switching is carried out without interrupting the use of FPU, SSE, and the AVX registers, there is also no need to preserve those during the context switches. This benchmark clearly shows and highlights the amount of extra operations that the kernel has to carry out when context switching a thread. A fiber can be context switched in about 10 nanoseconds, almost 120 times faster than a pin thread, and almost 400 times faster than an unbidden one. And although this thread doesn't really include a real scheduler, it's possible to keep the overhead of a scheduler to the bare minimum thanks to various optimizations if the fibers are pinned to the starting thread. It's also important to keep in mind that the scheduler needed for the fibers has really to be minimal because the scheduling is performed in a cooperative way. So a fiber at some point will say, hey, I don't have to do anything else, please process something else. So the scheduler doesn't need to be complex. Google implemented their own end-to-end scheduler with custom kernel patches quite a while ago. There is an interesting presentation about it. Their implementation takes about 180 nanoseconds. It's still 8 times faster than the kernel scheduler, although much slower than a fiber, but allows also cooperative scheduling. The huge advantage of this approach that really makes worth the overhead, I think, is that it's compatible with the existing POSIX APIs and tools. So if you use PS to list the threads, you will actually be able to list the user threads implemented with this set of custom kernel patches. So it provides quite some benefit. The second major optimization implemented in Cachegrand is related to strings. GCC and LLVM, they rely on optimized versions provided by libc. Therefore, every time the code has to perform, for example, a string comparison, it will have to jump to an externally provided function to carry out the operation. External calls come with a performance penalty, and the compiler can't really optimize the code. Having ad hoc optimized string functions that the compiler can inline can deliver quite a speed bump. Cachegrand carries out millions of short strings comparisons, both in the networking code and in the hash table as well, so it's really important to optimize it. From the chart, it's easily possible to see that a custom tailored implementation to compare up to 32 bytes with certain constraints in place can deliver from 2 to 4 times better performances. To be able to deliver high throughputs, I built a parallel hash table from the ground up for Cachegrand. The hash table, as mentioned earlier, is able to provide lock-free and wait-free get operations and uses localized locks for the set and the delete. Internally, it also uses a linear search algorithm optimized with SIMD and uses fake spinlocks instead of mutexes. And it also takes advantage of short strings optimizations, as mentioned earlier. So let's have a look. Data usually organized in a human-readable way, but the CPU really doesn't like it. The CPU has to perform a lot of extra operations when the data are not organized to fit how the CPU itself works. And that's a problem. And a linear search algorithm is a typical example from this point of view. Data can be arranged in a much better way, and the difference can really be dramatic. Instead of having a single data struct containing the hash, the key, and the value, and therefore an array containing those 3 pieces of information, the Cachegrand hash table uses 2 separate arrays, one for the hashes and another one for the key and the value. The algorithm first compares the hashes, and then if it finds a match, it compares the key, in both cases, of course. When the CPU accesses the cache or the memory, it always loads a cache line that's typically 64 bytes. Therefore, if, in the case of Cachegrand, all the hashes are sequential, it's worth to reduce the size of the hash down to 16 bits, taking the lower ones of the hash. So we can squeeze up to 16 hashes into a single cache line together. Actually, they will be 32, but we need some extra metadata per hash. So we get down to 16 hashes in a cache line. It's also important to keep in mind that the CPU prefetcher will always prefetch the next cache line, de facto allowing our algorithm to search over 32 hashes without further accessing the CPU cache or the memory. From the chart, it's easily possible to see that a data-oriented development in this context can deliver better performances, up to 150% actually, when the hash search is close, and even up to 300 in the worst case scenario. So definitely it's an optimization that it's worth it. Linear search, however, is slow and can be strongly optimized. And a common way to do it is to leverage SIMD instructions, as it's possible to compare with AVX2 a number of hashes just with a couple of instructions. With SIMD optimized linear search, we can easily get from 200 to 250% of speed improvement, of performance improvement over the simpler implementation. Let's move forward. As mentioned initially, the hash table relies on localized locks to avoid tombstones. The hash table is split in chunks, and each chunk is a cache line long, 64 bytes. This to take advantage of, as we mentioned earlier, of the way the CPU works. Most of the space has to be used for the hashes, but we need a bit of room for the metadata. So a chunk contains 14 hashes. Each hash is with its own metadata, so it's 32 bits. It means 4 bytes, and we're gonna have 14 of them. And then we have about 8 bytes for the chunk metadata, and those 8 bytes have to include also the lock. Nowadays the mutex are really fast, but they can easily send a thread to sleep, and we really want to avoid it. And also there isn't enough space to hold a mutex pointer in the metadata at the beginning of the chunk. We should use a translation table or an additional array just for the mutexes. Won't really be worth it. It would introduce some performance penalties. I came up with some fake spinlocks because they need only 1 byte to be implemented, and they don't send the thread to sleep if the spinlock is locked by another thread. Of course, on the other side, they waste plenty of resources, but the operations on the hash table last really nanoseconds, so it's absolutely acceptable. It's not a big deal, and they are fake because they can't really prevent preemption or context switching like it happens in kernel mode. From this chart, it's possible to see how the hash table scales vertically fairly well, although once that more than 16 threads are running in parallel, hammering it, the performances start to deteriorate, partially because of the context switching and partially because the CPU vector units get saturated. The current implementation is able to process more than 2 billion of inserts per second with 2048 threads adult Cachegrand, and I think most likely any software that is long-running software, server-side software, will never run those many threads. Cachegrand has been optimized to run 2 threads per core, so on a machine with 56 cores, it will run about 112 threads, so much lesser than 2048. As mentioned earlier, the get operations are lock-free and write-free, so they don't use atomic operations, only memory fences, and therefore they're able to perform really well. From the chart, it's possible to see that although we are facing the same scaling issues that we were seeing in the other chart, it still performs almost almost linearly in a constant time. In fact, up to 8 threads, the time needed to access a bucket is the same. with 16 threads, it increases a bit because this machine, the machine that I use for benchmarks, has 14 cores, 14 physical cores per CPU, and then over 16, clearly the context switching and the CPU vector unit saturations really plays a role. Another major optimization in Cachegrand is the Slab allocator. Memory allocators need to use lists to track the allocated and the freed memory, and because of the multi-threading, locks and or atomic operations are also needed, so performance really aren't great, although there are a lot of optimizations in place. The Slab allocator implemented in Cachegrand uses a fixed size blocks, uses huge pages, and therefore it's Linux only, and uses an ordered doubly linked list to achieve big O of 1 when allocating or free the memory. On Linux, the 2 megabytes huge pages are 2 megabytes aligned, so a simple module operations can return the huge page header where the metadata are stored. And the module operations is also optimized by the compiler. Because the pages of the huge pages are zeroed at the first access on a page fault, it's better to cache them to avoid this initial penalty. Otherwise, each time we will release and reallocate a huge page, the kernel will have to reinitialize the pages on the first access. The doubly linked list points to all the slots usable to hold the data in the huge pages. At the beginning of the list, there are the available ones, and at the end there are the ones in use. The Slab allocator also relies on pinned threads, and they are initialized on a specific core, and they are used only on that core. If a thread would move from one core to another with the current implementation, the Slab allocator would stop working. This approach grants good performances in a multi-threaded application and makes the Slab allocator NUMA aware. The huge pages, when freed, are reassigned to threads running on the cores on the same NUMA node only. They are never shared between different NUMA nodes. This is an overview of how huge page is organized by the Slab allocator. We can see that at the beginning there are some metadata, 64 bytes. Then there are a number of blocks or slots that are metadata. Then there is some padding, and then there are the actual blocks that are going to hold the data required by the application. Each memory block has a memory metadata associated. So the first block of metadata will match the first block of memory of usable memory for the data. Performance-wise, the Slab allocator is able to deliver a speed bump when objects are allocated and freed continuously, especially if no new huge page is required. It's also important to keep in mind that the Slab allocator avoids to fragment the memory. In a long-lived software like Cachegrand, that's something that longer term would impact the performances. So if it's possible, it's preferred to avoid it. The last major optimization in Cachegrand is the usage of I/O urling. It's a recent Linux subsystem, and it's able to provide true asynchronous I/O. I/O operations require syscalls, and switching forth and back between the kernel takes time. If you think about a network server that aims to manage, for example, 10,000 requests per second, it has only an average of 6 milliseconds per request. Having to read and respond to the request means that it has to perform not less than 20,000 system calls per second. What if we want to manage 150,000 requests per second? We get down to only 450 microseconds per request. And uncached syscall takes in average 300 nanoseconds. So this means that the software would spend about 90 milliseconds, almost a tenth of a second, forth and back between the kernel and the application for the syscalls. And it's a lot. The new subsystem uses a double ring buffer shared between user space and kernel space. A library is available to avoid having to deal with extra complexity. And once all the responses are processed and the request submitted, only one syscall is actually required. 0 with SQL. And IO ring also opens the door to direct NVMe access and eBFP, and actually more. It's really a Swiss knife from this point of view. And from this benchmark, it's possible to see that IO ring is able to provide between 7% and 25% speed bump, depending on the load. The difference is even greater when it comes to disk IO. Future planned improvements. The Slab allocator can really use some work. It can really take advantage of a more aggressive caching policy, as currently it keeps in cache only one huge page. Also, when allocating and freeing the huge pages and therefore all the slots used by the Slab allocator, a lot of work has to be carried out, and those algorithms can really be optimized and they can leverage SIMD instructions. Networking in general is a pain point when it comes to optimizations. The network stack provided by the kernel is not too fast, although in recent times it has really been improved in a massive way. But user-space networking can really provide quite a speed bump. And after some investigations, I decided that the best approach, at least for Cachegrand, would be to go down with XDP. And I know it may sound strange, but the main reason is because it's actually built into the kernel. On the contrary, DPDK is entirely user space. The reason for which being built into the kernel is an advantage is, number one, it has much better hardware support, and number two, it can leverage eBFP. This means that in combination with your ring, it can potentially, it's possible potentially using eBFP and your ring to read and write directly from the network layer from and to the storage layer. And this means reducing even further syscalls and improve the performances. Well, this is the end. The code that I used to generate the benchmarks is available on a GitHub repository that I created ad hoc for the summit. Some of the benchmarks are from the Cachegrand code base as well. The code is in the bench subfolder. You can follow the README to figure out how to build and run them. Well, thanks for listening and have a great day.
Thank you, Daniele. It's
thank you very much.
You can see there was a lot of craftsmanship put into building Cachegrand. So let me ask you a few questions. So you mentioned Cachegrand wants to be a Redis replacement. Why would you want to build one? What were the things you wanted to change?
I think that the Redis has a few major flaws, and the first and foremost important to me is not being able to take advantage of what the modern hardware and operating systems are able to offer. If you think about it, Redis is not able to fully load all the cores on a machine because it's running on a single thread. With the latest version of Redis, they started to use threads for the I/O, but still all the processing is made on a single thread. This is mostly because using multiple threads to access data structures requires, it comes with constraints, locks or atomic operations or memory fences. The second biggest flaw from my point of view is that nowadays we have NVMe flash memories. So we have a lot of space, very flash memories, and they are cheap, very cheap. If you think about an NVMe that is, I don't know, 250 gigabytes of space, it's the smallest one, well, the most smallest one you can find on the market. It's priced around 50, 60 euro. 256 gigabytes of memory for a server, they are slightly more expensive. So those are the two main flaws from my point of view that I wanted to address with Redis, with Cachegrand, and I'm really pushing on those.
Okay, thank you. And I particularly like the focus you put on benchmarks. In our previous edition this spring, we had Lawrence Stroud from King's College who was calling out how the benchmarks are actually biased. So I'm curious, what's your experience with benchmarks? Have you seen instances where they were incorrect?
Yeah, benchmarks, I think they are always biased, and it's really important, to test the optimizations at on-page, the optimizations on different hardware, and this includes different CPUs and also different generations of the same hardware, because there are improvements, but for example, and there are regressions. And the most noticeable one is just to make you laugh a bit. Intel in the few last series of CPUs made the pause instruction about 200 times slower. And this came with a consequence, because the kernel, the Linux kernel, was using the pause instructions for the spinlocks. So every time the spinlock was spinning, it was issuing a pause instruction that was 200 times slower. So they had to stop using them. And I really think it's really important to test everywhere and also on the cloud, because it always show up a number of problems.
Yeah, true. Word to the wise, as they say. Something else I learned from your talk was fiber. So my innocent assumption is that these are somehow lighter threads. But I was wondering, are they Unix only? You working for Microsoft, will your Cachegrand actually run on Windows?
Cachegrand will. Right now I'm focused on Linux. My resources are constrained. Let me start from the end. Windows absolutely support fibers. They are not Unix-only construct at all. Actually, you can imagine of a fiber like a function call, literally. The differences in terms of code implementation is almost null between the two. Fibers, you may have heard of fibers as coroutines or user threads. They are evolutions of fibers. But yeah, fibers are definitely not a Linux or Unix-only construct. They are supported by virtually all the hardware and operating systems.
All right. Thank you for teaching me that. And finally, I think the last questions we had is around, you build Cachegrand, you run a number of benchmarks. I'm curious how the vision that you set out for Cachegrand matches the reality. Which are the areas in which you think that you're doing better than Redis?
I on purpose didn't add the numbers for Cachegrand in the presentation, because I didn't reach the version 0.1 yet, so it's still not feature complete, and wasn't looking right to do a comparison. Not only because it can perform worse, but also because it can perform better, because features are missing. So to me, it was making little sense to add those kind of numbers. Although if you're curious, on the repository there are numbers, of course. So and of course there is all the codes that you can check out and run the benchmarks using Memtire benchmark. It's basically the standard tool that you would use with Redis or the other Redis alternatives on the market.
All right, super. Thank you so much for your time today, Daniele, and for the great talk. Looking forward to chat with you more at the panel discussion in 1 hour.
Absolutely. Yeah.